Vector decomposition. In many engineering and physics applications, it is necessary to decompose a vector into components relative to another vector, a line, or a surface. Specifically, we often need to determine the components that are parallel and perpendicular to a given reference. In this example, we will decompose vector A with respect to vector B. First, draw vectors A and B so that they share the same origin. Let the angle between the two vectors be denoted by phi. Next, draw a perpendicular line from the tip of vector A to vector B. This construction produces two projections. The normal projection, shown in blue, the tangential projection, shown in red. And let the magnitude of the tangential projection be denoted by AT, and the magnitude of the normal projection by AN. Now, define two unit vectors. A hat t, the unit vector in the tangential direction, which is aligned with vector b, and A hat n, the unit vector in the normal direction. Using these definitions, vector A can be expressed as the sum of its tangential and normal components. A equals to AT A hat t plus AN A hat n. This equation shows that vector A has been successfully decomposed into a component parallel to B and a component perpendicular to B. Now consider the right triangle formed by this construction. The hypotenuse is the magnitude of vector A, while the two legs are AT and AN. Therefore, we can apply basic trigonometric relationships from the definition of sine function. We have sine phi equals to opposite divided by hypotenuse, which gives AN divided by abs A, leads to AN equals to abs A sine phi. Similarly, using the cosine function, cosine phi equals to adjacent divided by hypotenuse equals to AT divided by abs A. We obtain AT equals to abs A cosine phi. Therefore, both component magnitudes can be determined directly from the magnitude of vector A and the angle phi. Finally, another useful trigonometric relationship is tangent phi equals to opposite divided by adjacent, leads to AN divided by AT. Magnitude of vector addition and subtraction. As we showed previously, vector A can be decomposed into the sum of two orthogonal components, one parallel to vector B and the other perpendicular to B. Therefore, A can be written as AT A hat t plus AN A hat n. Now let's determine the magnitude of the vector sum A plus B. So we have A like this. Since vector B lies entirely in the tangential direction, it can be expressed as abs B A hat t. Now adding the two vectors give this. Grouping the tangential terms, we obtain this equation. The tangential and normal components are perpendicular to each other, so they form a right triangle. Consequently, the magnitude of the resultant vector, here label it as C, can be found using Pythagorean theorem from this equation. Now, AN can be written as abs A sine phi and AT as abs A cosine phi. Substituting yields abs C like this. Expanding the square term gives abs C like this. Now, notice that the first and fourth term share the common factor square abs A. Factoring it and using the trigonometric identity, sine 2 phi plus sine 2 phi equals 1, the expression simplifies to this, and this is the well-known formula for the magnitude of the sum of two vectors. Using the same procedure, the magnitude of the vector difference can also be derived as this equation. The only difference between the two equations is the sign of the last term. It is positive for vector addition and negative for vector subtraction.